Okay, so we are looking for a unique solution of a differential equation. So the natural question to ask is there any connection of the order of a differential equation with that, with the uniqueness of a solution? So answer is yes. So for example, if you have, so answer to this is yes, and let's understand in arbitrary case. So suppose this is an initial value problem. Now we will give initial conditions to a differential equation and then we will get a unique solution. We will see how we will get it. So first of all, this type of problem, if it is stated like this, a differential equation with certain initial condition, then it is called as initial value problem. Now this function f, which is on the left hand side, is nothing but a differential equation. So for example, if I had a differential equation y double prime minus 3y prime plus 2y is equals to 15, say, then in this situation my f will be everything, and I will pull this 15 also on the left hand side because I am writing here f of this is equals to 0, and if I am comparing this with the equation, I have to keep everything on the left hand side, right? So in this context, my f will be y double prime minus 3y prime plus 2y minus 15. Now there is a difference here. When I was proving the linearity, I was taking the f only the function which contains derivatives and a y, but in this it's the entire thing because I am comparing it with this equation here. Okay, now initial condition, if you note here, how many derivatives are there in this function, in this general function? N derivatives, right? But if I see in this function how many derivatives, or basically what is the order of this differential equation? Order is 2, and order of this is n, right? Here order is n, and here this n is 2. Okay, so if n is 2, in that situation you have to specify how many initial condition. So if n is 2, 2 minus 1 is 1, so that means first derivative. So in that case you need 2 of them, right? So in this differential equation, if you want a unique solution, you have to specify 2 initial conditions. So y at a is equals to, and a can be any real number, say 3, and y prime at a is equals to, say 4, and this a we can think of as like a is 0 or anything, any real number. But now you can see this a is, you see anything like anything same here, this a is same, right? So x is same. Now you might say, well, y has to be also same. No, it can be different. So initial condition means you are specifying at x equals to a, what is the solution behavior? So what is for function y? So if my curve is like this and my x equals to a is, so in this case it's origin, so here is x equals to a. So at this point I want what is the value of function, and at the same time I want what is the value of its derivative, tangent, but exactly at the same point. So therefore we will always specify initial condition at the point a. Now if I give a problem in which I say f is a differential equation like this, and y at 0 is 3 and y prime at 1 is 4, is it an initial value problem? So let me ask you this question. Is y double prime minus 3y prime plus 2y is equals to 15 with y0 is equals to 3 and y prime at 1 is equals to 4 IVP? Is this differential equation an IVP? Is it an initial value problem? So for initial value problem, you need initial conditions and you need a differential equation. So now initial conditions are y at 0 is 3 and y prime at 1 is 4. Are they right? So is it an initial value problem? How many of you are saying yes? How many of you are saying no? Is this an initial value problem? I would say if you compare this differential equation and the pattern here, you need initial condition at only same point. So y prime at 1, the moment I said y prime at 1 is 4, this is not an IVP. I have to specify derivative also at 0. This point should be same, x should be same, this right hand side could be different, but x has to be same. Okay, so this is not. And if I say y at 0 is 3 and y at 1 is 4, that is also, this is a boundary value problem. Okay, so initial value problem is at initial point we are, so for example, if you have a heat equation or some equation which is specifying the heat flow, at that point you are specifying this exactly right now is a temperature of a water, exactly at this point. And then how will it change further? So this is an initial value problem. Okay, so now given that every function f which looks like this is a solution of a differential equation this. So it is given to you that this C1 and C2 being any arbitrary constants, this is a solution of this differential equation. This is given. You have to find out these arbitrary constants C1 and C2 by imposing extra condition which are y at 0 is 5 and y prime at 0 is 6. So now you are given initial condition. So first you are given a family of solution of a differential equation. Now with the help of these initial condition, we will determine the unique solution of this whole problem. Okay, so how we'll go for this? First, y at 0 equals to 5 means what? This is y. This is a solution of a differential equation. So y at 0 will be how much? If you plug in x equals to 0 here, what you will get? You will get C1 plus C2 is equals to, so this equation will give you C1 plus C2 is equals to 5. Okay, what about this one? Y prime at 0 is 6. So y is this, so what is y prime? 4c1 e to the power 4x minus 3c2 e to the power minus 3x. So y prime at 0 will be 4c1 minus 3c2. And this will be equals to this number 6. Okay, so we have two equations, two unknowns. So then how you will solve for C1 and C2? Yeah, elimination, that's it. So multiply by 3 this one and add in this one. So 7C1 is equals to so you all are with me, right? 21. So C1 has to be 3 and C2 will be then 2. So like this, now you have a unique solution of this differential equation. Second order differential equation, you need 2 initial condition. Third order differential equation, you need 3 initial condition. Fourth order differential equation, you need 4 initial condition. So the number of initial conditions are equal to the order of a differential equation. Okay, so this is a key. So the previous slide, when I was asking you here, is there any connection in the information which will give us unique solution with the order of differential equation? And answer was yes. So that is, the number of initial conditions should be equals to order of differential equation. So that's what you need. Okay, now if you have third order differential equation, you need y at 0, y prime at 0, y double prime at 0, and it need not have to be just 0. It can be at any point, but point has to be same. Okay, so this is the problem. Now this problem which I worked it out right now here is similar to your homework set problem number 'So I was saying like how you will find the constants and how will you eliminate the constants. Well, it's nearby but not very similar. Like you have this value of lambda, problem number 6, such that y equals to e to the power lambda x is a solution of this differential equation. So now if you plug in e to the power lambda x, which is a function in this differential equation, you will get a value of lambda in this. Now interestingly, once you get lambda, you know e to the power that is a solution of this problem, right? So just quickly, if you do the computation, you will get here lambda to be minus 5 lambda plus 6. So you will get lambda to be 3 and 2 in this. And the reason is, what is the double derivative of e to the power lambda x? What's the double derivative of e to the lambda x? Lambda x, everybody agree with that? Lambda square e to the lambda x, right? And then what is the derivative of, so I'm telling you the connection between this problem and the problem here. So you have here, you have to grab this, y double prime minus 5y prime plus 6y is equals to 0, right? So if y is e to the power lambda x, if y is e to the power lambda x, then y double prime will be how much? Okay, what is y prime? Tell me what it is. Okay, what is I double prime? E to the lambda x? Okay. Now if I plug this back in the differential equation, I will get y prime is lambda and y is 6 e to the power lambda x, and this is equals to 0. Okay, now how will I simplify this equation? Lambda square e to the power lambda x minus 5 lambda e to the power lambda x. How we will simplify this?
Can you take out e to the lambda x?
Very good. We will take e to the power lambda x form. Okay, now product of two functions, if this is 0, then either both of them has to be 0 or either of them has to be 0. Now we know exponential function is always non-zero. It can never be 0, right? Exponential function can never take a value 0. So this has to be 0. Now you are left with solving a polynomial. So second degree polynomial, what are the roots of this polynomial? No, it's 2. So that's why I said 3 and 2. The moment I came to know lambda is 3 and 2, then I know y equals to e to the power 3x will satisfy this differential equation. Right? Y equals to e to the power 3x will satisfy this differential equation. Y equals to e to the power 2x will also satisfy this differential equation. So what does that mean? E to the power 2x is also satisfying, e to the power 3x is also satisfying. What is the solution of this? Actually, you will see that the pattern of the solution which is written right here, c1 e to the power 4x plus c2 e to the power minus 3x. The reason this is a solution of this problem is because this is a second order problem. And for second order differential equation, you will have two constants. For third order differential equation, you will have three arbitrary constants. So that's the reason they are taking a linear combination of those two functions. And here also, if you want to write down the solution of this problem, linear combination of these two functions will be the solution of this problem. Okay. So this is a connection between this problem 6 with the problem which we just did now, did just now. Okay, now 7th also is a similar problem. Now let's move further. That's how you can get a unique solution. So what's a unique solution of this problem? So unique solution of this problem is C1 was with e to the power 4x, right? So yx is this and C1 is here 3. So 3 e to the power 4x plus C2 is 2 e to the power minus 3x. So this is a unique solution of this problem. So if initial condition is given from the class family of solution, we obtained a unique solution. One particular. Okay. Now we will try to understand how to solve these differential equations. So far we are just verifying a solution and see whether it's a solution or not. Now we really need to solve problems. Okay, so this is, first of all, this is which order differential equation? This is a first order differential equation. Okay. So we are focusing only on right now first order ODE, right? Okay, so this is so complicated and I would say a non-linear problem here, right? It's a non-linear problem, non-linear differential equation. Why is it non-linear? Can anybody tell me? Why is this differential equation non-linear? Is it non-linear or not? Right, y square y to the power 4 is making it a non-linear differential equation. So this is non-linear. Okay, I need to convert this equation in this format, and if I able to convert it in this format, I will able to solve it. So, so first let's try to convert it. So dy over dx. So I want here dy over dx, which is equals to y prime, is equals to like this. So okay, let me pull all these terms on the right hand side. So I will write it down. Y to the power 4 dx is equals to x cube y square minus 2 dy. Is it fine? I just pushed. I just maybe let's say this way. I added this whole term both the side. Okay. I added this term both the side. So I get this. Okay. What I want is dy over dx, right? So let's divide by dx. So we will get x minus 4 y to the power 4 is equals to x cube y square minus 2 dy over dx. Is it fine? Any question?
Isn't it 3?
Which one?
Yeah, it's
Oh, y square minus 3. That's right. This is 3. That's right. Now it's okay? Yeah, y to the power 4 is there, and this is cubic y square minus 3. Okay. So now dy over dx starts showing up, and I still have these functions here. So let me divide by the left hand side. So I will get here x minus 4 y to the power 4 divided by x cube y square minus 3. So is this okay? Okay. So then what is my fx and what is my gy? So okay, left hand side is this, that's fine. Now we isolated y prime from whole of this equation. So y prime is isolated with the expression here on the left hand side. I need to find out what is my f and what is my g in this expression. So what's f? What's f? Is it this? Because it's a product, right? It's a product. X minus 4 divided by x cube is fx, and y to the power 4 over y square minus 3 is gy. Right? So my function fx for this problem, fx is x minus 4 divided by x cube, and function gy will be y to the power 4 divided by y square minus 3. So is okay? So this differential equation I will call as separable. So any differential equation which you can write down in this format, in this form, then it will be called as separable differential equation. It has a special name, separable differential equation. Okay, and we can see here it's a second order differential equation, and we can, first order but non-linear differential equation, and we can still separate it like this. You will see this is very powerful. For non-linear problems, if you can separate them, then you can solve those non-linear problems. Okay, now let's understand how to solve these. Now same way you can isolate here y prime. I'll do it quickly now here. Dy over dx, if I divide, is equals to minus 4xy divided by x square plus 1. So here your fx will be negative 4x over x square plus 1, and gy will be y. So let's understand now how to solve these differential equation. So if they don't split out that easy, this problem is, we can't solve it. We can't solve this non-linear differential equation. Then we will go for numerical schemes, which will be the goal of upcoming lectures. The differential equation which we cannot solve, how we will figure out the solution of that problem? By computation, approximation. But then we have to understand why we are, like, suppose if the differential equation is not even having a solution and you are running a code on your computer, that's nonsense, right? So you have to first figure out through analysis whether solution exists, and once you know from a theory that a solution exists, you will run the code and find the approximation solution. Now solution exists part is different than explicitly writing some solution, right? So that would be, I will come to all these details soon, but let's see this differential equation. Dy over dx is fx and gy. So what we will do? We will separate it. Dy we will combine with gy, and fx we will combine with dx. Now you can see you can integrate both the sides. If you integrate both the sides, then you will have a constant of integration by fundamental theorem of calculus, and then you will simplify for your function y. That's a solution. Now, is this possible to do? Is this possible to go from here to here? When? That's exactly right. So if gy is 0, we are missing out solutions here. So when I divided by gy, I already assumed my gy to be non-zero. So I eliminated all those values of y for which gy is 0. We will take care of those solutions because they are also solutions and they are called as singular solutions. So the constant solution y equals to c such where gc is 0, they are singular solution. You can say constant solution or singular solution. And the general family of solution together with the singular solution will give you the whole class of a solution of this problem. Okay, so by this division we are finding general family of solution, and together adding with singular solution we get every solution of this problem. Okay, so in this division we have assumed gy to be non-zero. Okay, now let's solve this simple problem which we guessed in the last lecture, right? So you told me y prime equals to y, solution is c e to the power x, because all constant multiples of exponential function will satisfy this. And you also told me that y prime equals to ky, solution will be c e to the power kx in the last class. Now, why is this a solution of this differential equation? So first of all, is it a separable differential equation? Is it a separable differential equation? What do you think? So what is fx? What is gy? Right? If it has to be separable, then you can rewrite this in this form. dy over dx is g y and fx, right? So what is fx? Okay, what is gy? Y or ky, right? K is just a constant. So fx is 1. You can multiply with 1 with anything, right? And you just remain same. So it's a separable differential equation. So here gy is ky and your fx is 1, or you can take fx to be a constant function k, whichever way you want to take it. Okay, so now this differential equation we want to solve. So what I will do, I will isolate y, or put y all together and x all together. So now by this kind of writing, I am assuming gy to be only k. I am not assuming gy to be ky, right? I am assuming in this splitting, I am assuming this to be just y and this to be k. So now if I integrate both the sides, I will get on the left hand side ln of absolute value of y. On the right hand side I will get kx plus constant of integration. Okay, now we have to solve for y. And what did I assume here in this step? Did I assume anything in this step? I am dividing by y, so I assume gy to be non-zero. That means I assume y to be non-zero, right? Okay, in this step. Now exponentiating both the side, you will get yx is equals to e to the power kx plus c. right? Now I can say that yx is equals to c hat or c tilde, whichever way I want to write it down, is a family of solution of this problem. Now why is this correct? So instead of writing that above solution, I rewrite this as in this form. This is same as writing, if I write down this one, it is e to the power kx times e to the power c, right? By rule of exponents. So this e to the power c, I merge this and I named as a new constant c hat times e to the power kx will be a family of solution of this differential equation. So you might question at this point, will it affect the uniqueness of a problem, uniqueness of a solution, right? If I was given an initial condition in this problem together with this differential equation, I have say y at something, then if one of you take this form and another one take this form, will you get the same solution? Are you getting what I'm asking? Or what's the confusion? Maybe I only said this confusion. Okay, you know what? Don't worry about it. If you're not able to think about that particular question, just first of all, just focus that this is a general family of solution, and we assume y to be non-zero. If y is 0, then it will satisfy this differential equation. So y equals to 0 is a singular solution. It's a singular solution of this problem. Okay, so if I were given here initial condition, so let's do this part as well. So suppose together with this problem y prime equals to ky, I am given here y at 0 is 5. Now this is a first order differential equation, so I only need one initial condition, right, because of first order. Okay, so I will stop here. I won't write down the information about derivatives. Now let's plug it. So if the solution, if one of you obtain this form e to the power kx times e to the power c, and another one is working out with this form c hat e to the power kx, then y at 0 from the previous function, we will get what? E to the c will be equals to 5. And here it will imply what? C hat is equals to 5. Okay. So if e to the c, so if c hat is 5, you will plug back the c hat value back in the function to get a unique solution, right? You will plug back this value here. So you will say, okay, yx is equals to 5 e to the power kx is a unique solution. K is given, by the way. K is given in the problem. So this is a unique solution. Okay. So now if e to the power c is 5, then what is this little c? Ln of 5, right? And if ln of 5 you plug it here, you will get again 5 e to the power kx. So whichever form of a constant you take doesn't matter. Eventually you will get a unique solution if you are given an initial condition. So whatever form you place your solution, Doesn't matter too much. What matters is the initial condition. Okay, so this is so far we figured out initial condition will give you unique solution. Now let's understand more about separable differential equation. So in this homework, you is problem. So which differential equation in this whole homework is separable? So problem number 4 is separable, right? Okay. Is problem number 3 separable? Problem number 3, is it separable differential equation?
Yes.
Right. Is there any other way to do problem number 3 apart from separable differential equation idea? Problem number 3 is saying dy over dx minus 6x is equals to 4 e to the 2x, right? You want to find out the function y which will solve this differential equation. So what will you do? So you have here y prime minus 6x is equals to 4 e to the 2x, right? You can say, okay, y prime is 6x plus 4 e to the 2x. What is your main goal? To find what? What is unknown here? Y of x, right? Function of y, right? Y is unknown. And you need to find y. How will you proceed? Suppose you don't know any method. You just know calculus. Integrate both the sides. With respect to which variable? X. Right? So if you integrate both the sides with respect to x, you will get y. Isn't it same as what is separable method? Because dy over dx, if it is 6x plus 4 e to the 2x, and if you take this dx on the right, integral here will be y, and here it will be integral of 6x plus 4 e to the 2x dx. And then you will have a constant of integration out of it for me. Right? And you can integrate this function very easily. 6x square over 2 and then e to the power 2x over 2 cancels out and plus c. Right? So y of x, you got it. You got a solution here. So depending on the problem, some problems you have to think a lot, but some you don't. Okay, given a solution, getting back a differential equation. You are given a solution, but you are not given a differential equation. How will you proceed? So for example, let's see problem number 8. Problem number 8. You are given a solution, but you are not given a differential equation. Well, I did give you multiple choices, but suppose you don't see all of them. Just hide it. Don't see them. So given a solution, how will you get back to a differential equation? So in all these differential equations, what is the point which you see in common? Differential equation will never contain what? Differential equation will never contain ... constants. Differential equation will never contain any constants, like arbitrary constant. It will never contain. If constant is there like 15, a specific constant, that's fine. But like c, which can take any value, differential equation will never contain that. That will mean what? There's so many family of differential equation. Which one are you solving for? Okay. So somehow you need to get rid of the c. And how will you get rid of the c? You solve for this c. When you solve for the c, what will you get? Okay, let's solve for the c. This problem. What will you get when you solve for the c? Y squared plus 2 divided by x cube, right? We are currently working on problem 6, problem number 8. So now what? How will I get rid of c? With respect to x. Just take derivative of both the side with respect to x. C will be gone and you will get differential equation. And note that y is a function of x. So that's how you will get the differential equation. Now, if you have two constants, you have to work a little more. You have to get rid of both of them. And in process of getting both the constant eliminated, you have to make use of, somehow you have to solve for C1 and C2 and eliminate them. And the moment you eliminate C1 and C2, you should definitely end up in getting second order differential equation, because two constant can only come in second order. And if there are three constant, then it will be third order differential equation. And if only one constant, you should end up in first order. You might keep taking derivative, but you have to give only first order differential equation. Okay, so let's now move on to this another class of differential equation. I will get back to this special type of one logistic problem, but before that I will introduce another type of differential equation. Is it big enough in the back? Okay. Y prime plus px okay. Y prime plus pxy is equals to qx, right? So this is a first order differential equation. Is it separable? Is this differential equation separable? So let me give you value of px and qx, and you can play around with that. So y prime plus say 2xy equals to 5x square. Is it a separable differential equation? But try to convert it if you can. So you will do what? You will first isolate y prime, right? Push everything on the left except y prime to the right. So you will get 5x square minus 2xy. So you will get y prime equals to 5x square minus 2xy. Now can we find fx and gy in this? No. So this is not a separable differential equation. It's another class of first order differential equation, but not separable. But they are what? What are they? Any other speciality about this differential equation? Is it linear or non-linear? Everybody? It's linear or non-linear? It's linear. Because why? because y function is sitting with a degree 1. Y prime is sitting with the degree 1. So this differential equation is linear. X can be x square, sine x, cosine x, anything. So any first order linear differential equation can be written in this form. This is a very powerful statement which I am making. Any first order linear differential equation can be written in this form. Any first order linear differential equation can be written in this form. Okay, so every first order linear differential can be converted into the above form. If it's a linear, then you can find out px and qx and you can put it in this form. Okay, so what is px in this differential equation? If you compare it from the above, px has to be -1 and qx has to be -2e to the x, right? Coefficient of y is your px. This is also called as standard form. In order to understand the solution process of this differential equation, we always try to emphasize this thing that we always try to keep this px on the left hand side to be on the safer side, so that we don't make any mistake in the signs. Okay, so px is this, qx is this. What is px here? Qx also e to the x, right? Okay, so this is a standard form of a linear first order differential equation. Now the goal is to solve this differential equation. The first natural thing you will ask yourself, okay, suppose somebody gives you a problem to solve. How will you proceed? Usually, how will you proceed? This kind of like a mathematical kind of different kind of lesson that I'm trying to put here. Okay, given a problem, what do you try to do with that? Like, if I ask you, okay, I want a solution of this problem. You know the solution of what? Separable. You know how to solve separable. So maybe the first thing you should try to see is how can I convert, or can I convert this into separable? And you just now said you can't convert it. But is there anything else which I can do with this differential equation so that I can convert it into separable? So let's understand this slowly. I can see from the left hand side, I have this two type of function y prime plus pxy. In order to, so let's, I want to convert my left hand side into dv over dx. And whatever will be left on the right hand side will be my fx. And if I able to convert in this form, it will be separable then, right? Then you can solve it. But the mystery here is how to find this v. And what is this v? So you have to combine the left two terms. In order to combine the left two terms, is there any pattern in the left two terms? Y prime plus pxy from calculus. Y prime plus some function times y. And I want to write it down as a derivative of certain function v. So this is a pattern y prime. This is the main crux of this problem. Y prime plus px times y. There might be a function here, could be a function here, which we can divide it out. Maybe something. So if there is a function here y prime plus a function times y, does it remind of anything like d of what can be d of which function can give me this kind of stuff? Y prime plus some function times y. Y is also coming, y prime is also coming. So if I take a derivative of which function so that I get maybe something near to this, not exactly this. Can you guess something like which is nearby? Maybe you don't get exactly this, but some similar kind of form. If you do here, if you multiply some function u with y, say, and if you take a derivative, what will you get? U y prime plus u prime times y, right? So that kind of is giving this kind of form, right? Y prime, u y prime plus u prime times y. We don't know this u as well right now, but we are solving for this mystery v, right? We are trying to think of the v which can give this kind of expression backwards. Okay, so we will break this into smaller steps. Let's multiply u with y, and that's what I was thinking. Then you just multiply this equation by ux so that you can start getting some similar form. Okay, px ux y equals to ux qx. We still don't know q, but our goal is to try to find v. So okay, this is something we are getting now. And if I see backward, u y prime I am getting, okay, that's fine. Y u prime I should get, okay. And this should be equals to some fx. If u times y will become my v, right? So this is combining here. So basically first, what is u? I can compare here these two terms. So I'll get px ux to be equals to u prime, or I will rewrite it as px times ux. Can we solve for this u? Px is given to us from the problem, right? From the first order given linear problem, px is known to us. So if you have a px, can you solve for u? This equation. This u is magical here. And this u has a name also for this kind of differential equation. The moment we get u, we will multiply u with y, and that will be our v. And then we have converted the whole problem into duy equals to fx, where fx is nothing but your ux times qx. Okay, so this is your fx, this whole thing is your fx, and you have to just find this u. The moment you have u, you have v. Okay, so now how will you find u? You just now told me what is the solution of this problem. Is there any connection between this problem and this problem? Almost same, only thing is here you have a constant and here you have function of x. But The same idea will work here. Ux is nothing but e to the power integral px dx. As you have here e to the power k times integral dx, which is e to the power kx, which you said very quickly, e to the power kx, but it was actually integral dx. Okay, so this is u and it has a name, it's called integrating factor. It combines the left hand side two terms. Integrating factor. And it will be helpful in solving the homework problem, the last ones. So this is integrating factor. Once you have integrating factor, you multiply with y. So duy over dx is your ux times qx, which is fx. Now this is a separable differential equation. And u is e to the power integral px dx times yx. So once you have that, this is a separable, and you use a separable technique, separating it and integrating it, and you solve for v. Once you have v, you have u, you divide by it and you get y. That's it. Okay. So for example, if you have this problem, how will you solve this problem? dv over dx equals to fx. Vx is equals to integral fx dx, right? So then this means ux times yx, because v is nothing but this, is equals to integral fx dx plus a constant of integration, and therefore ux you already know is this, you have yx. And ux is e to the power integral px, and that's the solution of this problem. And fx is what? Fx is ux times qx. So u is integrating factor, you plug u and you will get then the solution of this problem. Now this, I have written down here the steps of integrating factor. This is ux only in the slide, and then you multiply throughout by ux and merge two terms. So which rule did we use here to get v from your calculus? To get this v, okay, forget about this process. To get this v, which rule did we use here? I multiplied u with y, right? And I differentiated it. So I got what? When I differentiated it here, u multiplied with y and differentiated it, and then I was comparing it in this step. So which rule did we use? Product rule is a key for solving first order linear differential equation. Using integrating factor, you can convert first order linear differential equation into separable. So I said to you that you cannot, like this example you said, oh, we cannot convert into separable. Here you said to me this one, no, this is not separable. First order linear differential equation not separable. You said to me when we started out on this slide. But then I said, is there a way I can make it separable? And answer is yes, using integrating factor. If we solve for u and multiply throughout in this differential equation, we will make it separable. Integrating factor converts a first order linear differential equation into a separable differential equation, and then you just are solving separable differential equation. Okay, and to get integrating factor we used product rule. Okay, so by product rule we get u, we basically thought about u, and then solving this differential equation we get integrated. Let's solve now first order linear differential equation, one example, and then we will stop so that you can able to work on this homework. So let's solve this problem. Y prime plus xy equals to x. Y at 0 is 2. Linear first order differential equation, right? Px is what? Px is x. Qx is x, right? Now integrating factor ux. E to the power integral px dx. E to the power x. Now you will not put a constant of integration in here. Never put constant of integration in integrating factor. We can go over to this y, but let's finish this problem first. So we will not put a constant of integration here. This is integrating factor. Now we will multiply by integrating factor throughout this differential equation. So if I multiply it, I will get e to the power x square over 2 y prime plus x y e to the power x square over 2. Then I will have x e to the power x square over 2. So I multiplied with integrating factor throughout. Now what magic is happening here? What is this left hand side two terms? D by dx of what? D by dx of what? So y times e to the power x square over 2. Is it right? This whole left hand side is nothing but derivative of y times integrating factor. Because if you see this function times y prime plus y times, what is the derivative of e to the power x square over 2? E to the x square over 2, and then derivative of this is 2x divided by 2, which is x, right? Can you all see this calculation? This is important here. Whole left hand side is merged into the function y times integrating factor, and this is equals to x e to the power x square over 2. Now integrate both the sides. So what is the integration of this function here? What's the integration of this? Quickly, it's easy. Substitution. Do substitution. Z equals to x square over 2. dz equals to 2x over 2 dx. So that means x dx will go away. So it's integral of e to the power z, which is e to the z, right? So e to the power x square over 2 plus a constant of integration. And left hand side is y e to the power x square over 2. Now divide throughout by this, you will get y is equals to 1 plus c e to the power minus x square over 2. This is y of x. So general family of solution. But what is the initial condition? Y at 0 is 2. So that means 2 is equals to 1 plus c, which will imply c is equals to 1. So you have here yx is a unique solution to be as unique solution of this differential equation is 1 plus e to the power minus x square over 2. That's it. So given a differential equation, you first find the integrating factor. Once you have that integrating factor, you multiply throughout in the differential equation. And then once you multiply it, it automatically converts the left two terms into the function y times e to the x square. Where did I get this? Because I divided this whole equation here by e to the power x square over 2. So this get cancelled, here got cancelled, and c times e to the power minus x square over 2 will come. Because dividing this whole equation. Okay, so this is the whole key here. How can we merge the left hand side two terms into just single function? This is the key for first order linear differential equation. Okay, that's it for today, and I'll post this recording.